All right, today we're looking at different acids and bases. So let's continue with acid strength. What are the factors influencing acid strength? One, the bond. For example, we saw HI versus HCl yesterday. HI, the stronger acid, got the weaker bond. But there are other factors influencing acid strength as well. And so if you take a look, and we'll list them here, but if we take a look at nitrous acid, versus nitric acid, nitric acid has some weird formal charge stuff going on here. But we might think that the acid strengths are the same because this is an HO bond, this is HO bond. HO bonds have about 400, a little over 400 kilojoules per mole for the bond energy. And so you'd think that these are comparable, but it turns out nitric acid is a strong acid, nitrous acid is a weak acid. So what accounts for the difference in acid strength? And that would lead us to the second factor. And so we look at bond strength first, and then after bond strength, those are both HO bonds, we would look at bond polarity, or just polarity, the polarity of the H. And you might think, well, the polarity shouldn't be a factor here because oxygen has electronegativity of 3.5, hydrogen is a 2.1. This is the same, 3.5, 2.1. So if we look at delta EM, the difference in electronegativity, we get the same number. And so the delta EM is the same, but the difference in acidity is significant. And so we have to dig into the structure deeper then, because if we look, this is a hydrogen bonded to oxygen bonded to nitrogen. Well, this is the same thing, hydrogen bonded to oxygen bonded to nitrogen. And so it doesn't look any different. However, the two nitrogens are different, because if you look at this nitrogen, there's no formal charge here. Over here on this nitrogen, we have a positive formal charge. And so I asked you, did I ask you the other day, what's the electronegativity of fluorine? Right? Fluorine is a 4.0 on the Pauling scale. But if I had fluoride, is fluoride equally as electronegative as fluorine? No, the electronegativity of fluoride is a lot less. Well, this is a nitrogen with a neutral charge, and this is nitrogen with a positive charge. So nitrogen with a positive charge is going to be more electronegative. Just like fluorine with a positive charge, I'd expect this fluorine to have much higher electronegativity than this. And this should be the least electronegative. And so it depends on the charge on the particular atom. And so in this case, it's clear that this nitrogen is positive, this nitrogen is 0, and therefore this nitrogen is going to have more pull on the electron density. And what's going to result is something called the inductive effect. Are you guys familiar with the inductive effect, right? And so the inductive effect, we're going down here. There's also a difference in, what causes this charge on the nitrogen, and that is the extra oxygen. Now, when we look at charges are going to be playing a vital role in how electronegative a species is. That is the pull on the electron cloud that particular atom has. And when we look at the charge on an atom, we have to recall that there are two main ways of counting the charge. What are they? The two main ways of counting the charge are formal charge and oxidation state. Yeah, that's it. And so let's take a look at the oxidation state between the two nitrogens. Do these two nitrogens have the same oxidation state? And the answer is no. What's the oxidation state on this nitrogen? Oxidation state, yeah, is 0. Is that correct? No, it's not. Formal charge would be 0, but the oxidation state's not 0. The oxidation state is +3. +3 is correct. How did you figure that out, Eric? Yeah, oxygen beats nitrogen. Because in oxidation state, what do you assume? Oxidation state, you assume, yeah, the bonds are 100% ionic. In other words, you assume winner takes all, so this ends up being +3. And so the formal charge is 0. The oxidation state is +3. You see, those are the two extremes in charge. It could be 0 or it could be +3. What is it though? You know, what is it? The reality lies somewhere between. So, did you guys have a chance to review oxidation states? I know this morning they didn't figure out how to do oxidation states in formal charge. Let's take water as an example here. This is just for oxidation state and formal charge. Formal charge assumes what? 100% covalent. That means the bonding electron cloud here is totally symmetric. It's not polarized in one direction or another. And so it's very symmetric. In other words, the bonding electrons here are evenly distributed or evenly shared between hydrogen and oxygen. And this results in 0 charge. And so this gives us the formal charge. Oxidation state, though, it wouldn't be like that. For oxidation state, there would be no. In fact, for oxidation state, who gets all the electrons? Oxygen takes all the electrons, leaving hydrogen with nothing. Actually, we can both sides. And so if oxygen gets all the electrons, then that leaves oxygen with 8 electrons and a -2. Oxidation, hydrogen gets nothing and is +1. So those are the two extremes in how we distribute the electron density in a bond. But the reality is where? Is it 100% covalent? No. Is the bond 100% ionic? No. The reality is it's somewhere in between these two extremes. And somewhere in between these two extremes, you know, what we say is it's this. You know, oxygen is more electronegative, but hydrogen is not going to lose all the electron density. And so, you know, because hydrogen's electronegative is still 2.1, which is pretty decent. And so it's not going to be 0 like this, and it's not going to be -2. It's going to be somewhere in between 0 and -2, the charge. Since we don't know what that number is, we just assign it a symbol. We'll just call it delta minus. Delta minus means it's some partial charge. In fact, this partial charge is probably not going to go beyond -1. And on hydrogen, we don't know. It's not 0 and it's not +1. It's somewhere between 0 and +1. Maybe it's like +0.6 or something, +0.7. And so that's what we call a partial positive charge here. And so these are the three. I told you there are two. There are two because what we do is we border it. We border it on one extreme and then the other extreme. And then the third, we think about where it should lie in between the two extremes. You know, the extreme would be formal charge. Sometimes the formal charge is correct. Sometimes the oxidation state is correct. I mean, if the compound is really covalent, and it's a 100% covalent bond, then this is correct. If it's really ionic, this would be correct. If it's somewhere in between, then this is the correct picture. But we still use the numbers nonetheless. So this would be +3 in terms of oxidation state. However, this is what? +5. And so if we compare this, if we compare a +5 nitrogen versus a +3 nitrogen, which one is going to have a stronger pull on the electron cloud? The +5. And so this is the inductive effect. The inductive effect is this nitrogen is highly electronegative, pulling electron density away from this oxygen. Normally oxygen pulls the electron density away from the nitrogen because it's more electronegative, but this is +5. And so this is going to have a much stronger pull than it normally would. It's not to say that nitrogen is going to take all the electrons from oxygen, it won't. Which is, in turn is going to make this more polar. And so in terms of polarity, this hydrogen is a lot less positively charged. This hydrogen is a lot more positively charged. This hydrogen is a lot more covalent. This hydrogen is a lot more ionic in terms of percent ionic character. So polarity, if you're a base like hydroxide, which hydrogen would you be more attracted to? So hydroxide is a base, it's a strong base, Bronsted base. And so are you going to attack the weaker acid or will you attack the stronger acid? Attack the stronger acid, there's going to be a bigger attraction here. We got a full negative charge on oxygen being attracted to a larger positive charge here. And so this is why when we're doing Bronsted acid-base reactions, we pick the strongest. The strongest acid reacts with the strongest base. And so this would be the strongest acid, the strongest base. If I had a mixture, of nitrous and nitric, the nitric would react first. So that's another factor. You know, when the bonds look like we have the same bond strength, the bond energy, then we look at polarity. The more polar it is, the better. The more polar it is, the stronger the attraction it should have towards bases. And there's one other thing we look at, and that's the stability of the conjugate base. The conjugate base would be the product, so this is the stability of the products. The more stable the products are, the bigger the driving force, and the stronger the acid. So let's take a look at this as an example. All right, let's see. Okay, we're going to just look at various bases. So let's look at base strength. You know, the stronger the base, the less stable it is. The weaker the base, the more stable it is. And when we look at the conjugate base, which is the product of the reaction, and look at the conjugate base, what makes a base more reactive? And so we can do a quick comparison here. We can compare hydroxide versus water. When we compare hydroxide versus water, which one should be a stronger base, hydroxide or water? I would pick hydroxide. Why? Hydroxide because acid is positive. This is just a positive-negative interaction. And so if I have a full negative charge here versus a partial negative charge here, the full negative charge is going to be more reactive. It's just got more negative charge density there. And so hydroxide versus water, hydroxide is more reactive, and therefore it's less stable. Okay, so let's look at some other bases here. So hydroxide's more basic. We're talking about Bronsted base strength. If I get into Lewis, it complicates things. So looking at Bronsted, hydroxide, let's go with hydroxide versus water, hydroxide. Hydroxide versus the FO minus ion. And so this one would have a negative formal charge on the oxygen. Fluorine would be 0. Which one should be more basic? Hydroxide or the FO minus ion? Yeah, actually, hydroxide should be more. Basically, it's because of the F. What happens is hydrogen versus oxygen. Hydrogen is a 2.1, oxygen is 3.5. So hydrogen versus oxygen, oxygen has a higher electronegativity, which is going to pull the electron density, even though this oxygen is negatively charged here. Now we're looking at fluorine. Fluorine versus oxygen. Well, let's compare the electronegativity of hydrogen versus fluorine. Fluorine's much more electronegative. If fluorine's much more electronegative, what's going to happen is fluorine's going to pull more of the electron cloud towards itself. As it pulls more of the electron cloud, it pulls in more of the electron cloud density towards itself. So what happens is it distributes this negative charge over a wider volume. In other words, when we're looking at the stability of the conjugate base, we look for charge delocalization. The more we can delocalize that charge, and there are two ways. One, we could just make the charge smaller. And so here, this is a full negative charge, this is a partial negative charge. Well, a partial negative charge is less concentrated negative charge, making it weaker. Here, this is a full negative charge, this is a full negative charge. So both of these have a full negative charge. However, this one's going to be more delocalized because of fluorine. Fluorine's going to suck the electron cloud towards it more than hydrogen does. And so as fluorine sucks the electron cloud density away, more of that negative charge density on the oxygen gets pulled towards fluorine. Whereas over here, oxygen sucks the electron cloud away from hydrogen, and thus concentrating the negative charge density on oxygen here. And so because of this, we say that this would be stronger. This would be weaker. And we call this the inductive effect, just like this. You know, the inductive effect here is this pulling of the electron cloud, pulling of the electron density here. And so what we have here is what we call charge delocalization by the inductive effect. Fluorine's going to be pulling the electron density away. And so charge delocalization by the inductive effect is one. And we can look at another example here. All right, so hydroxide wins out. This is going to be weaker here. Now let's take a look at something that has a comparable electronegativity to hydrogen. Let's take carbon. Carbon and hydrogen's electronegativity are similar. Carbon's 2.5, hydrogen's 2.1. The 0.4 difference is not so significant. And so carbon electronegativity is comparable to hydrogen, so we don't expect much of a difference in the electron cloud here and here, and therefore we would expect these two to be comparable in terms of basicity. However, if I start adding some stuff to the carbon, let's go ahead and add in fact, let's make this a acetate. So now what we're going to do is we're going to look at hydroxide versus acetate. Which one's stronger? You might think they're both the same strength, because if we look oxygen to carbon, oxygen to hydrogen, electronegativity is not that different. But these are quite different though, because if you look at this carbon, what's the formal charge? The formal charge is 0. So the formal charge doesn't really tell us anything. What's the formal charge on this hydrogen? 0. So, actually, yeah, formal charge is 0. But we don't want to stop at formal charge. What else do we look at? Oxidation state. So what's the oxidation state on this carbon here? +3? That's correct. +3 is correct. The oxidation state on this carbon is +3. That's good. What's the oxidation state on this carbon? -. -3, yep. So do you see these two carbons are totally different? These two carbons are quite a bit different. In fact, with a +3 carbon, that's going to make this carbon much more electronegative than it normally is. Carbon normally has an electronegativity of 2.5, but this is a +3 carbon. And a +3 carbon is more electron poor, so it's going to suck some of the electron density away from here. Versus this hydrogen is just a 0. You know, the oxidation state is +1, but still it's not so significant. And so we'll have some inductive effect going on here. And so there'll be some inductive effect because the carbon's going to suck some of the electron density away. You know, normally if it's carbon versus oxygen, oxygen wins. But now this carbon's going to put up more of a fight because it's at +3. And so it isn't going to be as lopsided as it normally is. And so here, we'll have some inductive effect which will help delocalize the negative charge into the structure. Do you see that? And so we would expect, again, we expect hydroxide to be stronger, and we expect acetate to be weaker because of the inductive effect. But it turns out that acetate is significantly weaker because there's one more factor here when we're looking at charge delocalization. And this is even more significant. The inductive effect turns out to be smaller in terms of impact on strength, base strength, than resonance delocalization. We can actually draw, if you look at this structure, acetate, we can draw a resonance form for this. In this resonance form, what happens is this negative charge jumps from this oxygen up to this oxygen. That would be the resonance form here. And so a resonance form, is this going to indicate that the negative charge jumps back and forth between the two oxygens? One instance it's here and the next instance is here and just goes back and forth? No. It doesn't work that way. Does it mean that this goes from a double bond to a single bond to a double bond to a single bond? No, nor this one. We know that there's a problem with these. This is a problem with valence bonds, so we fix this. We fix this with something. This comes after the fact. After we've generated the Lewis structures, we come up and correct it because the true structure doesn't have the negative charge jumping back and forth. And it doesn't have the bonds shrinking double and extending single. The true structure should be or similar to the combination of the two. The combination of the two, do you recall the name of that? No. The true structure is gonna be a mix of those, and it's gonna be a 50-50 mix because we have two contributing structures of equal weight. And so we end up with nobody remembers the name? The name, it's called the hybrid, resonance hybrid structure. And the hybrid structure is going to be a 50-50 mix. In other words, it's going to look something like this, where the pi bonding electrons are smeared out over both bonds like this. And the lone pair, that extra lone pair, is smeared out over both. And that results in a formal charge. What's the formal charge on each oxygen now? Rather than the -1 spread out over two, each one's going to be negative -0.5. Good. So the formal charge is -0.5, -0.5. And so the impact of resonance delocalization is huge. We drop the charge on the oxygen from -1 to -0.5, which makes it a lot less reactive. Not only that, Did the formal charge, well, the formal charge didn't change on this carbon. The formal charge is the same, as is the oxidation state. The oxidation state on this carbon is still +3. And so not only do we have resonance delocalization, but we also have the inductive effect, and this carbon +3 is going to pull electron density towards it. And so this negative charge is going to drop even further, not hugely, but a little bit further from -0.5. And so we have a combination of resonance delocalization and inductive effect, making acetate much more stable and much less reactive than hydroxide. Hydroxide is much more reactive and a much more powerful base than that. And so these are the factors that we look for in doing that. And strong acids are going to hydrolyze water. Water is going to come in and pluck that proton off easily. Weak acids just partially hydrolyze or partially ionize. And so let's do a quick example here of this. Sulfide versus oxide. Which one's a more powerful base? Which one's a weaker base? This will just be for Bronsted. So which one's a stronger base, sulfide or oxide? Sulfide is a strong. Both of these are strong bases. Both sulfide and oxide are strong bases. Which one's stronger? Oxide's stronger. Why is oxide stronger? Charge density, right. Oxide is stronger because of charge density. Both of them have the same charge. It's just how it's distributed. In oxide, you have a -2 charge concentrated in a smaller volume, and sulfide is a -2 charge in a much larger volume. This only works for Bronsted. This only works for Bronsted because the acid is always the same. The acid atom is always hydrogen. But it doesn't always work for Lewis. If we're doing Lewis, we have to do HSAB. Does anybody remember what HSAB stands for? Hard, soft acid bases. It turns out these are different. Sulfide's what we call soft, oxide's hard. And so sulfide turns out to be a more powerful base if the acid is soft as well. If the acid's hard, then oxide turns out to be a more powerful base. But that's more complicated because in Lewis acid bases, the acid's not always the same, as I said. In Bronsted, it's easy. The acid is always the same. It's H. And so we can do these simpler strength comparisons. All right, so what we're going to do today is we're going to do some pH measurements. And pH is going to tell us, the acidity or basicity of these solutions. But we can actually calculate the pHs of these solutions. And so, for example, what solutions are we looking for today? We're looking at water. We have two types of water in this lab. We have DI water, and we have tap water. Now, the tap water, we're not going to take a pH measurement now, but the DI we will. The DI water, what does DI stand for? A lot of people say DI stands for distilled, but that's wrong. This DI water is not distilled, deionized. We have ion exchange columns, things that take ions out of the water. What's better, you think, DI water or distilled water in terms of purity? Deionized? Well, it's because of the process. The deionization process is typically used. Distilled water is usually better. It depends on how high purity water you want. Usually, if you're doing stuff that requires very high purity of water, high purity water, you don't just use a DI. In fact, I did a series of experiments where I needed exceptionally pure water, and so I remember this. These were when I was at UCLA. I would take a 5-gallon polyethylene container. It had to be plastic. It couldn't be glass because there were certain ions in glass that could get leached into the water, which we didn't want. We used polyethylene, and the stuff that could get leached from the polyethylene, it wouldn't impact my experiment. It was, you know what the experiment was? The experiment was sodium, quantitative sodium analysis. Now, sodium's such a pain because everything contains sodium, and it's so easy to contaminate your solutions. And so we had to, I had to use the ultra-high purity water. The ultra-high purity water was, you take DI and you distill it. Not once, but you distill it twice. So it goes through 2 distillation apparatus, and then it's hit with UV, and then you use it. It's very expensive water. You know, to distill it twice costs a lot of energy, and then all the equipment involved. Even DI water is not so cheap. Our DI water is kind of expensive. But we're going to check the pH of DI water. Assuming that the water is pure, what should be the pH? Yeah, the pH should be 7. We don't have to do a calculation for this. It should be 7.00 at 25 degrees C. Right? At 20, because we did the KW calculation the other day, and we saw that. But what happens? Do you think it's 25 degrees C today? I don't know. No, it doesn't feel, it feels a little colder than 25 degrees C. And so we have to worry, if it's a little bit colder or a little bit warmer, is that going to impact this reaction here? And so at 25 degrees C, we said that there's going to be about 4 out of a billion. You know, there's some kind of energy cutoff here. And so at 25 degrees C, there's a small fraction of molecules that have sufficient energy to break bonds, form bonds in this collision. Boom, big collision, you got hydronium hydroxide. This reaction is highly unfavored, but you know, if there's enough energy, it'll happen. So what happens if the temperature is higher? Let's see. If the temperature is higher, what will happen? Will the pH change, or will the pH stay the same? It's just pure water. Well, the pH is going to change. If the temperature is higher, there's going to be more molecules. You know, this is at a higher temperature. We broadened the distribution. What kind of distribution is this? Yeah. Thermal distribution. That means the fraction, maybe it was 4 out of a billion, now it's a much larger fraction of molecules that have sufficient energy to react. At higher temperatures, the hydronium ion concentration goes up, goes down, or stays the same at higher temperature. You know, because KW is at 25 degrees C, and so in other words, does K change with temperature? Yeah, and so at higher temperature, K goes up. As you'd expect, this is endothermic in the forward direction. And so if K goes up, then the hydronium ion concentration, it was at equilibrium at 10 to the minus 7 molar, is now going to go up. It's still neutral, because even if it goes up, the hydroxide is going to go up in the equal proportion, and if the hydronium and hydroxide are equal, it's neutral. So it's still neutral, but the pH is going to be lower or higher? The pH is going to be lower. And so at higher temperatures, the pH of pure water should go down. At lower temperatures, the pH of pure water should go up. The pH of pure water should go up because the fraction's smaller. We're going to produce less hydronium. And so water is neutral at pH 7 at 25 degrees C, but if we're not at 25 degrees C, what is the neutral pH? We can calculate it, because we know how K varies. We can just use thermodynamics to figure out how K varies with temperature. And so we could calculate it, but that turns into a nightmare. it turns into a nightmare because, you know, what's neutral? Well, you got to ask, what is the temperature? And then I'll tell you what neutral is. And so, since this is a nightmare, what we do is this. You know, with electronics nowadays, all we do is this is in the old days, all we do is we adjust the temperature knob, and all the temperature knob does is reset it. And so as the temperature changes, you adjust the temperature knob, and that'll bring the pH, even if it goes down or if it goes up, it'll just bring the pH back to 7. And so the easiest thing to do is this. The easiest thing to do is to use electronics. And nowadays you don't even have to turn a knob. The electronics will automatically compensate for changes in pH as the temperature fluctuates. So if the temperature goes down, you don't want the pH of water to change. You want the pH of water to stay at 7. And that goes for everything else. Otherwise, you know, this becomes a big headache. And so basically, we're going to compensate for the changes in pH due to the changes in kW by using electronics. And so pH meters nowadays, you don't have to think. And you don't even have to measure the temperature. You know, when I was doing pH readings before, I'd have to measure the temperature and then adjust for the temperature. We don't have to do that anymore. You just stick the probe in and just read the temperature. That's it. And so it's much easier, but the problem is that people think that kW doesn't change. It does change, and the other thing is that people think that the amount of hydronium doesn't change with temperature. It does change with temperature. We're just artificially keeping the pH at 7 when we're taking our measurements. And so here, I don't care what the temperature in the lab is. You know, what I'm going to do is I should measure pH 7. My probe should, and the electronics should compensate. All right, now what are we going to do next? So that's water. Well, the next solution we're going to do is sodium chloride, AQ. Now, sodium ions, are those acidic, basic, or neutral? Are those proton acceptors, proton donors, or?
Just frosted.
Hmm?
Just frosted.
Just what?
Frosted.
Oh, I'm talking about Bronsted. Is that a Bronsted acid, Bronsted base, or neither? This is neutral. This is neutral. Chloride. Chloride's a base. But what do you know about this base? It's too weak to hydrolyze water. If it's too weak to hydrolyze water, then we call it neutral. Therefore, neutral. You know, chloride's capable of accepting a proton. If it accepts a proton, it would form HCl. You'd be done with that. And so the pH of sodium chloride should be 7.00. The sodium ions and the chloride ions don't contribute any additional hydronium or hydroxide to solution. But let me do a quick aside here. Now, chloride's a base, and so you would expect bases. You know, bases hydrolyze water to produce hydroxide. And since chloride's a base and water, that's base hydrolysis, is given by the Kb. Kb stands for base hydrolysis, which is just base and water. The Kb for this is just equal to HCl times the hydroxide divided by the chloride. And then we would think, what's the value for this? You know, what is the number? You know, because this number is going to tell us. You know, it should be 0 because it shouldn't really hydrolyze water. It doesn't hydrolyze water, it's neutral, right? It should be 0. But, you know, when we're looking for Kb values, we aren't going to find them. Usually what we find are Kb tables. And so Ka tables. Ka tables are available. And there are some Kb tables, but they aren't very comprehensive. There's just very few entries in there. And so Ka tables, the Kb tables are missing. Well, it turns out we don't need the Kb tables because there's a relationship. What we're going to find are the Ka tables, and then we have to calculate our Kb values from the Ka values. And the way we do that is by using this relationship. If A and B are conjugates, then Ka times Kb for the conjugate pair is equal to Kw. And so we could see this by just taking the generic acid, HA. HA, acids hydrolyze water to form hydronium. That's our Ka. And the Ka for this is going to equal the hydronium times A minus, which is a generic anion. And so Ka will be the hydronium times A minus divided by the HA. Now Kb is its conjugate. What's the conjugate base of HA? The conjugate base of HA is A minus over here. And so A minus, is being a base, will hydrolyze water to produce hydroxide. And so this is going to form HA plus hydroxide. And the Kb equation is going to be HA times the hydroxide. So HA times the hydroxide divided by the A minus. And so A minus cancels, HA cancels, and that leaves us with Kw. So Ka times Kb is equal to Kw. And so if we want the Kb value for this, the numeric value, then what that is, it's going to equal, the Kb will equal the Kw divided by the Ka. So it can be Kw divided by the Ka, but it has to be the Ka for the conjugate. And so if I'm looking at chloride as being the base, its conjugate acid would be HCl, so it would be the Ka for HCl. Do you recall what the Ka for HCl is? This is going to be Kw. Do you recall what the Ka for HCl is off the table? There wasn't a number. What did we call it?
Very large.
It was called very large. The Ka for HCl was very large. So if we take Kw and divide it by a very large number, this should approach 0. And so this is why we don't expect much here for hydrolysis. And so, to make a long story short, sodium chloride should be neutral, the pH should be 7. And the only thing hydrolyzing is water itself. You know? And, that's it. Now, what's next in the lab today? I'm going in order of the experiment, I think. But the next one isn't such an easy calculation to do. And that is sodium carbonate. Let's just do that. Sodium carbonate. If I look at sodium ions, those are neutral. And we're looking at 0.1 molar sodium carbonate. This is 0.1 molar sodium chloride. I think it's 0.10 molar. Let's go with 0.10 molar. You give us 2 sig big. And so the sodium ions are neutral. How about carbonate? Are carbonates proton donors, proton acceptors, or neither? Proton acceptors. And in fact, carbonate can accept 2 protons, not just 1, but 2. And so what that means is this is a dibasic base. Dibasic bases can accept 2 protons. Tribasic bases can accept 3 protons. This is the same thing as monoprotic, diprotic, triprotic, kind of thing for acids. And so this is a dibasic base. Well, what do bases do? Bases hydrolyze water. And so if I have base mixed with water to hydrolyze, form hydroxide. And so let's go ahead and do that. We got some carbonate, and this is going to react with H2O liquid to form. Okay, carbonate's a proton acceptor, so we only want to do one proton at a time. Even though it's a dibasic base and it can accept 2 protons, we just do one and then see what we have left over. And this is going to form a hydroxide. And so what we need is we need the Kb value for carbonate. The Kb value for carbonate is equal to the Kw, which everybody should memorize, 1.0 times 10 to the minus 14. We're going to assume that we're just going to keep things at 25 degrees C. So we've got Kw and Ka for what acid? For bicarbonate. And so we just have to look up the Ka value for bicarbonate. And we're going to find the Ka tables in our book. And a few Kbs, but not enough Kbs. Most of the Kbs we're going to get, we're going to have to calculate. So this is table D3, appendix D. And so we'll just go on. Here's bicarbonate. So I have bicarbonate, and then this is the Ka value. No, there's no Kb values here. Just the Ka. So the Ka for bicarbonate is 4.7 times 10 minus 11. Write that over here. 4.7 times 10 minus 11. Let's continue with our calculation here. And so the Kb is Kw 1.0 times 10 minus 14 divided by Ka for bicarbonate, 4.7 times 10 to the minus 11 gives us a Kb value of what? So 1 times 10 to the negative 14 divided by 4 times 0.7 times 10 to the negative 11. I get 2.12. Actually, I'm only out 2 sig bigs. 2.12. Maybe I'll throw in one more. 2.127 times 10 to the minus 4. And so this is my Kb value here. So what we're going to do is we're going to figure out what the pH is, the hydronium ion concentration. So we'll set up our ice table. What we assume is nothing's happened. So this is going to be 0.10 molar. This is going to be 0 molar and 0 molar. And then let's figure out how much hydroxide there is. And if we can figure out how much hydroxide, then we can figure out the pOH. And once we get the pOH, we can figure out what the pH is. All right, so can you go ahead and finish this calculation here?